golden brown, texture like sun, lays me down. With my mind she runs throughout the night.
Okay, so here's an example of a problem we could get that again calls for us to use the double angle identities. Okay, so we're going to solve this equation here for all solutions within 0 to 2 pi. Okay, so the thing is, we need to expand this thing out into something that we know. So let's just write down the three options we could use. So we could use cosine squared t minus sine squared t. That's option A. We could use the one where we have 2 cosine squared t minus 1, or we could use 1 minus sine squared t. Okay, so we're going to decide which one to use based on what we see on the right-hand side. Okay, so on the right-hand side we have a cosine t, so that doesn't really relate to sine t at all, so we're just not going to use that. We're not even going to introduce another kind of trig function there. And the same goes for this one here. I don't think we should introduce another like sine function or anything, so let's choose this one. Let's just replace the left-hand side with 2 cosine squared t minus 1, and on the right-hand side we'll just have this cosine t there. Okay, let's subtract this guy over to the left-hand side. Okay, so when we do that, we're going to get an equation like this. 2 cosine squared t minus cosine t minus 1 is equal to 0. Okay, and this might look a little bit familiar. It looks kind of like a quadratic function, and it basically is. Okay, where cosine t is kind of like our x, sort of. You can consider it. So what we can do is just factor this. Okay, so 2 cosine t goes here, and cosine t goes there. It's kind of like just breaking it up into 2x and x, right? And then we want to have a negative in the middle there, so we're going to put the negative 1 over here and the positive 1 right there. Okay? So from here we could just say, okay, well, either this equals 0 or this equals 0. So we could say, well, cosine t is equal to negative 1/2, or cosine t is equal to 1. Okay? And for both of these, we could get, well, for this one we get t is equal to 0. Okay? And then it says for solutions within 0 to 2 pi, so we don't need to put that plus or minus 2 pi k. Alright, because we're only going around the unit circle once. How about for this one? We get that t is equal to what? Let's look at the unit circle. So cosine, which is our x value, is equal to negative 1/2 when we're at, this would be 2 pi over 3, or 4 pi over 3. Okay, so those are the solutions we get from that kind of like segment, or that portion of our quadratic. Okay, and that's it. Those are our three solutions on the interval from 0 to 2 pi. Okay, so now what I want to do is let's take a look back at one of the versions of our double angle identities. The cosine 2 alpha, where alpha is an angle, right, is equal to 2 cosine squared alpha minus 1. So let's say we want to solve for this. Just get it by itself. So we're going to add 1 to both sides. So we get 2 cosine squared alpha, and I wrote an x because I like x's. So anyways, 2 cosine squared alpha is equal to cosine of 2 alpha plus 1. Let's divide by 2 on both sides. Divide by 2. So we basically just get that cosine squared alpha is equal to cosine of 2 alpha plus 1 divided by 2. And this here, lo and behold, is something that we call a power reduction identity. Okay? And the reason being is that it's kind of self-explanatory in the name, but it just takes, let's say you were, for some reason, you came upon an equation and you ended up with a cosine squared alpha in your answer, and you don't want that squared exponent there. So you want to reduce it. You want to reduce the power on the cosine. See how here it's like cosine to the first power? Yeah, so we reduced that power by just replacing it with this whole thing. Okay? And likewise, we can take, let's see another form of our cosine 2 alpha is equal to 1 minus 2 sine squared alpha. So if we were to solve for sine in this case, we would just get 2 sine squared alpha is equal to 1 minus cosine of 2 alpha. So we could also get that sine 2 alpha is equal to 1 minus cosine of 2 alpha divided by 2. So this also is the other power reduction identity that we could use. Alright, so we could also Let's see. Let's say we're starting with this power reduction identity, where cosine squared alpha is equal to cosine of 2 alpha, and then plus 1 over 2. So for some reason, just because we feel like it, basically, say that theta, some new angle, okay, is equal to 2 times whatever our alpha is, okay? So in this case, alpha would then be equal to theta divided by 2, okay? So alpha smaller, theta is bigger. Okay, great. So let's say we want to replace the alphas in here in terms of thetas, okay? So let me just erase that line. That's a little confusing. So if we replace those, we get cosine squared of, instead of alpha, now we're going to get theta over 2 for some reason. And I'll show you why, where this is headed. So then we get cosine of 2 alpha, which is 2 times theta over 2, which just gives you a theta, plus 1 over 2, okay? Let's say we want to square root this and get cosine of theta over 2 by itself. So we get cosine theta over 2 is equal to a plus or minus square root of cosine alpha plus 1 and then divided by 2. Okay? So this thing here, this is called a half angle identity. Okay? And half angle meaning that when you have cosine of half an angle, then this is the formula that you could use in order to figure out what cosine of your half angle is. Okay? And we can do the same exact thing with sine. Let me just draw a little line here. So let's say we start with the sine squared power reduction identity, right? And that was by taking 1 minus cosine 2 alpha and then over 2. Okay, let's say we replace, again, that alpha with theta over 2. So we get sine of theta over 2, and this is being squared, is equal to 1 minus cosine of theta divided by 2. So then sine of theta over 2. So the half angle identity for sine is going to be plus or minus the square root of 1 minus cosine theta and then divided by 2. Okay, so both of these together, the thing that I'm boxing now, as well as this one down here, so both of these are called our half angle identities. Okay, and I'll show you how to use it in an example on the next slide. Okay, so this question asks us to find an exact value for cosine of 15 degrees. So it's like, okay, wait, hold on. So here's our unit circle. We know 30 degrees, but that's like basically the lowest or the least angle, or the lowest angle that we know, that we're familiar with, is 30 degrees, and 15 is half of that. So wait, hold on. So let's say we can rewrite 15 degrees as 30 degrees over 2, right? So this is kind of like a half angle. It's going to require some kind of half angle formula. So in this case, our theta is equal to 30 degrees, okay? And our formula for cosine is plus or minus the square root of cosine theta plus 1 over 2. So we're just going to plug in theta is equal to 30 degrees, so cosine of 30 degrees, which we do know and we're familiar with, right? So cosine of 30 degrees is just radical 3 over 2. Okay, so this is going to be plus or minus the square root of radical 3 over 2 plus 1 and then over 2. So we're just going to do a little bit of math here and say, okay, so this is the square root of, and we'll say, well, this is radical 3 over 2 plus a 2 over 2 and then all over 2. Okay, so this is plus or minus the square root of radical 3 plus 2 and then over a 4. Okay, and we can just keep that in there, and now we just have to decide, okay, is this plus or minus? And if we just look at our picture and kind of our intuition, we can say, well, 15 degrees is here, and cosine, which is like our x value, that's positive. So we're just going to pick the positive answer. So our answer is ultimately going to be the square root of 3 plus 2 and then over 4. And that's the exact value of cosine of 15 degrees using the half angle identity. Alright, so that wraps up our concepts video on double angle identities. I hope that helps, and I'll talk to you in the practice problems video if you watch.